So this is the screen you're seeing. And thank you all for coming. It's I think this is our best turnout since we went back to hybrid meetings, and I don't think it's got anything to do with me. I think I know why we've got a good turnout, and we'll be hearing about that in a few minutes. I'd like to start with an acknowledgement. We respectfully acknowledge the territory in which we gather as the ancestral homelands of the Beothuk, and the island of Newfoundland as the ancestral homelands of the Mi'kmaq and Beothuk. We would also like to recognize the Inuit of Nunatsiavut and Nunatukavut and the Innu of Nitassinan and their ancestors as the original people of Labrador. We strive for respectful relationships with all the peoples of this province as we search for collective healing and true reconciliation and honor this beautiful land together. And hopefully, we think a little bit about what that means. We've all heard lots of land acknowledgements, and many of us come from different places in the country. So where I'm from is not, you know, I live here now, but I come from a place where there's a different peoples, but same kind of issue. So maybe everybody can think about that a little bit. So I have a couple of announcements, and then I want to say a little bit about the AstroImaging contest. So calendars are being distributed, and do we still have people that need to pay, or we're getting close to that? Anyways, payments go electronically to payments at St. John's RESC.ca. And our meeting in January will be Randy talking about the solar eclipse that's coming up in April 8th. And we are at the point now in the AstroImaging contest where the page with the submitted entries has just gone live today. And you'll be getting the link for voting probably tomorrow or the next day. And so I'd like to thank Marcellus and Gary for setting the contest up, and Craig for doing the page. And I'm going to switch to my browser. See if I can find that and just show you what there is there. Browser. Yes, he is. Okay, so we're not there yet, so I'm going to close. Oh, okay. Go away. I'm fighting with the little bar up above. Here we are. Okay, so the poll that you're going to be getting looks like this. We're going to ask you to put in your email just so we can tell who's entered. And then we've got 4 entries in the wide field, and so you can vote for them there. We have 6 entries in solar system and 12 entries in deep sky. And to see them, you can go to the center webpage and click on AstroImaging contest. Nope, I need to update this. There we are. Entries, and you can actually see the entries along with some information, except I've removed the name of the actual photographers. And so the deadline for voting is January 8th. It's a Monday. That should let us sort of wrap things up at the next meeting. I'd like everyone to vote, please, because we need enough votes for it to be significant. And people who do astroimaging know about needing lots of signal to noise, so we're after that. And so are there any questions about that? Again, thank you to everybody that's contributed to getting this going so far. And I'm gonna I'll ask for your patience as I click back and forth. It's always a bit of a challenge. Okay, Are you seeing that now, Randy? Okay, so there's the information, but you'll get the email with all the necessary links, and you can already see the images on the web page. We have some visitors, so I'd like to say a little bit about membership. These meetings, it's the third Wednesday of every month, except in the summer. They're open, the public meetings are open to everybody, but if you join, you become, there are some benefits. You join a supportive community. We have a chat group, RESC NL Talk. You have to be a member to join that. And it's very nice. Images appear up there. People discuss observing opportunities and lots of mentorship up there. A lot of advice that people get. So if you're a member, I'd encourage you to join that. You can contact Randy at info@stjohnsresc.ca to get added. We have publications, the journal and the handbook. We have low-cost equipment rentals. In the summer, maybe we have observing sessions. We'll hear some more about that. And members get a monthly bulletin and a weekly newsletter. Okay, so with no further ado, I'll get to the sort of main event of the evening, except for eating the treats afterwards. But this is the more important one. This is at least the third talk that Anna's given us, but it's my great pleasure this time to introduce her but I don't have it on here, as Dr. Anna O'Grady, and that happened in the summer in July or sometime. And so Dr. O'Grady was and many of us have seen that coming for many years, so we're happy that we've gotten there. McWilliams postdoctoral fellow at Carnegie Mellon in Pittsburgh. You just heard she completed her PhD and that was astronomy and astrophysics at U of T this summer. She did her BSc in physics and applied math here. And her research involves observations of stellar populations in nearby galaxies. And she uses those observations to put constraints on rare or unknown class of massive stars. So we've heard a little bit about that in the past. We're going to hear some more now. So I'm going to stop sharing this one, and I'm going to start sharing this. Actually, I'm going to stop sharing that for a second because we want to.
Okay, is this okay? And then, okay. And can I just confirm for people online that you're seeing this? Perfect, awesome. Okay. All right, we are good. Okay, well, first of all, I want to thank Mike and everyone at RASC-NL for the invitation. I'm thrilled to be back here again. This is and will remain to be for me an absolutely wonderful way to cap off my year in astronomy. I'm very privileged to have opportunities to speak at many different places, giving public talks or at conferences all around the world, but it is not an exaggeration to say that this is my favorite place to speak. And I always look forward to capping off my year in this way. So this year I have something a little bit different to talk to you all about. If any of you remember my previous presentations, you'll note that the title slide is really different colors this time. It's all yellows and blues. So what's up with that? I'm going to be talking to you about what has begun as the final chapter of my thesis, but is the beginning of a very big venture that myself and my collaborators, who I have listed here, as well as future collaborators, are venturing into the world of binary star evolution. So yeah, the main topic of my research now is on binary star systems. So, would that be useful? That would be awesome, actually. Yes, thank you. So, binary star systems. So if you're a fan of anything sci-fi, the first thing that probably comes to mind, and I've spoiled this slide already, but is this the binary star system of Tatooine in Star Wars, where you have planets that orbit around not one, but two suns. There we go. Yeah. So yeah, so when you say binary stars, a lot of people know what you're talking about because of the scene. But of course, this is science fiction or science fantasy. What about actual science? What does it mean for stars to be in a binary system, and how does that differ from being a single star? Let's go over just a quick overview of single star evolution first, so that you have that in your head, so then I can tell you how binary stars are different. And first talk about this traditional picture of massive single star evolution. So my research focuses on massive stars. So these are stars that are much bigger than our own sun, 10 or 15 or even larger times the mass of our sun. And what I'm showing here is a Hertzsprung-Russell diagram. If you've been to one of my talks before, you've definitely seen one of these. They're pretty ubiquitous in stellar astronomy, where we're plotting the temperature of the star against the star's luminosity, or how bright it is. And each of the black lines that are going across here, this is a track that is describing how a star of various masses, so 12, 15, 20, 25 times the mass of our sun, how that star begins its life on the main sequence, which is this black line here, and then evolves over time, how it changes in its luminosity and temperature as it grows up, essentially, and reaches the end of its life. So we can see on this diagram, as I said, the main sequence where stars are burning hydrogen into helium in their cores, but eventually stars will run out of hydrogen in their cores and they'll evolve off into other stages. So they expand, they get larger, they get colder and more luminous, and they very quickly cross this area of the diagram known as the Hertzsprung gap. And it's called a gap because when you look at large populations of stars, and you sort of populate this diagram with real stars, there's very few in this area. And the reason that there's very few is that stars pass through this area quickly. When they're expanding, they're doing it on a very short time scale compared to when they're just sitting and doing nuclear burning in their course. So stars cross this gap quickly, and then they go on to hang out over here, and these are known as red supergiants. So stars that are, 12 to say 30 solar masses will end their lives here. They'll get over to the red supergiant branch and they'll stay there. They'll sit there, they'll burn helium in their cores, eventually will reach heavy element burning, and they will explode as hydrogen-rich supernovae. If you have bigger stars that are 40, 60, 100 times the mass of our sun, those stars are so large, they have very strong stellar winds that will strip off parts of their outer hydrogen envelope until you are left looking at the much hotter interior of the star. So on a Hertzsprung-Russell diagram, that evolution is portrayed as the star is going towards the hotter end. So you can see in a track like the 60 solar mass track, it gets out close to the red supergiant branch, but then it turns around and it goes over here. And these really big stars end their lives over here. And when they explode, they're hydrogen poor supernovae. They don't have any hydrogen left because they've sloughed it all off of themselves in strong stellar winds. So this is sort of the old view of massive star evolution. You're a single star, you evolve by yourself. If you're kind of small, you become red. If you're kind of big, you become blue. You explode with a lot of hydrogen or not very much, depending solely on that mass. However, there are several, and I mean several, uncertainties and unanswered questions that our observation of massive stars has essentially brought this view into question, basically showing that this single star view of massive star evolution is not correct. And I'll just highlight one that will have some relevance later. This is another Hertzsprung-Russell diagram, so still temperature and luminosity, and still showing a range of stellar tracks. And the colored in areas on this diagram, these represent areas where, if you assume single star evolution, this is where we expect supernova to happen. So as I was saying, you can either have red supergiants exploding with a lot of hydrogen left, or you can have blue supergiants exploding with very little hydrogen left. That's where we expect the supernova to happen. The dots and crosses and arrows on this diagram, are where, when real supernovae have exploded, we've gone back into archival images, found the star that exploded, and figured out its properties. So figured out how hot and how luminous was that star when it exploded. So these dots, and especially these crosses, are the location of stars when they explode a supernova. Can you see the problem? These guys shouldn't be exploding. These are stars that explode as yellow supergiants, not red and not blue. And this is extremely hard to explain with a single star evolving on its own. You shouldn't have a single star just blowing up in the Hertzsprung gap for no reason. And in particular, these types of stars blow up as hydrogen-poor supernovae. So they have a little bit of hydrogen. They're not totally stripped, but they don't have a whole lot of hydrogen. So I will come back to this diagram, but suffice it to say, this is just one example of how single star evolution is not sufficient for explaining all that we see in the universe. And thus brings me to binary star evolution, which is when you have two stars that are orbiting one another. And the most important way that binarity can affect stars is if those two stars interact with each other. Now, you can have some binary systems where the stars are far enough apart that they're effectively single. They're orbiting around each other, but they never interact with each other. They just go about their business, evolving as if they were single stars. But you can have examples where binary stars either end up exchanging mass or end up merging. And these interactions can both occur on the main sequence or when stars are older and they're beginning to evolve. And this is really important because studies have shown that the latter two options are actually far more common. When you have a binary system, 70% of those systems will interact in some way over the course of their lives. Only 30% of binary systems are far enough detached that they're basically single stars. 70% will undergo some type of envelope stripping, accretion, or even merging. And I want to talk a little bit more about envelope stripping because that'll become important later, just to explain what's going on there. So if you think about how binary systems might interact, how they might transfer mass, or they might even merge, stars won't just randomly move closer together in space. There has to be some sort of action to move stars, and stars just sort of randomly decreasing their orbits isn't something that really happens. However, instead, what happens is instead of stars moving closer together, is that one star expands as it evolves. We know that stars like our sun swell up from dwarfs up into giants or even supergiants. They increase their radius by a whole lot. And if one of the stars expands enough, its outer layers will reach a boundary that's known as the Roche radius. And what this radius essentially is, it's the boundary that divides on which side gravity from one star is stronger than gravity from the other. So if you're inside this part of the dashed line here, the gravity from the blue star is stronger. But if you're on the other side, then gravity from the yellow star is stronger. And essentially what happens is this blue star, as it evolves and swells up into a supergiant, its outer layers will cross over this boundary, and the outer layers of gas and plasma will no longer be gravitationally attached to its original star. It will instead have gravitational attraction to the companion star, and you will have this sort of tidal mass transfer. So this is what we talk about when we talk about envelope stripping. The other star will slowly sort of pull the outer layers off of the companion star. This is a little bit more of an in-depth example. There's a lot going on in this diagram, but I'm going to walk you through it. But this is just another nice little schematic of what's going on, where you have two stars, but one of them is a little bit more massive, so it evolves more quickly and it expands. When it expands, it overfills its Roche radius and starts to pour extra material onto its partner. And you eventually end up with a star that has been entirely stripped of its outer hydrogen envelope, leaving behind an incredibly hot, dense little star, excuse me, and a new companion star that, as you can see, is a little bit bigger than how it started. So what's going on here in this diagram? This is still a Hertzsprung-Russell diagram, like I was showing you before. So temperature on this axis and luminosity on this axis. And the red line here represents this first star. So if we follow it, you can see it follows a very normal life. It leaves the main sequence. It starts to expand. And right around here at point B is where it reaches the point where it starts to transfer mass onto its companion. And that has a dramatic effect immediately. The star plunges down in luminosity. It becomes super dim and then shoots back up. This is because when it's transferring mass off of itself, it loses its thermal equilibrium. So it's literally all disequilibrated. It's a little bit freaked out. And by losing its outer envelope, you reveal the hot interior portion of the star. So it goes to extremely hot temperatures and comes over here as a strip star. The secondary star, which is the one here, is represented by the blue line. It has a little bit of a calmer time. It's just accepting mass onto itself. But you can see that where it began as a low luminosity star, when mass transfer starts, it essentially restarts its life as a star of a higher mass. Mass transfer for the secondary acts as a bit of rejuvenation. It makes it so a smaller mass star can live the life of a higher mass star, but without losing a certain amount of lifetime to it. If you've ever heard of blue stragglers, so galaxy clusters, where you have this nice turnoff of the Hertzsprung-Russell diagram, but then there are these blue stars that shouldn't be there before, this is the explanation for this. It's a form of binary interaction where stars that began their life as smaller stars get kicked up into higher masses and are these little blue straggler stars. So that's just one example of how binary evolution can massively influence the life of a single star. This is another example. Back to this diagram here. This is the example using single star evolution. Over here on the right, the colors have been expanded. This is what happens to our predictions for supernova explosions if you include binary star physics. And what do you know? The colored areas have increased. We can now explain the explosion of yellow supergiants if you include binary star physics. What essentially happens is they get stuck there. These are stars that would normally have evolved into red supergiants, but they get stuck. Instead of continuing to expand and getting colder as they expand, they start to lose mass and they just get stuck in this one area of the Hertzsprung-Russell diagram, and that's where they end up exploding. And finally, binary interactions are also absolutely crucial to forming gravitational wave events, much like the neutron star merger that I'm sure that you heard a whole lot about back in 2017. This is a canonical diagram that shows up in a lot of people's talks. I won't go over it a whole lot, but just basically pointing out that from having two regular main sequence stars, in order to get to the point where you have two neutron stars merging together, you need to have 1, 2, 3 separate cases of binary interaction. So it's essential for causing one of the most interesting phenomena that we've seen in the universe to date. Okay, so binary interactions are really important and they can do all these cool things that I've described. But how common is this? You know, am I just describing, you know, binary systems? You know, they're not very common, so these things only happen every once in a while. Does anyone want to take a guess? You can shout out your answers. If you take all of the massive stars in our galaxy, so all of the big stars that are 10, 20 solar masses and above, what percentage are in binary systems versus being just all by themselves?
90%.
90%?
80.
80? Any other guesses? 10%?
95.
95, 99? Okay, you all have great answers. This is excellent. So an absolutely incredible amount of work has gone into figuring this question out. This is a bunch of papers that I've listed. So if you consider just on the main sequence, between 70 to 100% of massive stars on the main sequence are in binary systems. And this percentage goes up as you get to higher masses. So if you consider like 50 and 60 and 70 solar masses and above, 100% of them, all of them are in binary systems. So binarity is absolutely ubiquitous for massive stars. it matters for all massive stars, and therefore it matters for all aspects of their evolution. And as I mentioned before, of binary systems, which we know that 70 to 100% of massive stars are in binary systems, 70% of those systems undergo some type of interaction. So between 60 to 80% of all massive stars will undergo binary interaction at some point in their life, which makes understanding all of the weird physics that goes into all of this stuff absolutely crucial for understanding the grander picture of our universe. So we know that 70 to 100% of massive stars are in binary systems, and 70% of those will undergo some kind of interaction. About 20 to 30% will actually merge when they're on the main sequence. So when they're still young stars, they're still burning hydrogen into helium in the cores, they'll merge together then. But that still leaves a really big chunk of the pie for when stars are older, when they're in more evolved forms, when they come off of the main sequence. So, oh, I'm missing a plot here. Okay, there's supposed to be a Hertzsprung-Russell diagram right here, not doubled text, but I will just continue. So what we end up doing, I will just go back really quick to have this. So what we end up doing is we look at the fractions of binary stars at different evolved parts. So as I said, there's been all this work put into understanding what the binary fraction, or what percentage of stars are in binaries, what the binary fraction is on the main sequence. So we can understand what types of interactions happen if we understand what the binary fraction is for evolved systems like red supergiants or blue supergiants that are later on in life. Because those are the stars that interact later on and don't merge right on the main sequence. So from this, some constraints that we have on the binary fraction, if you look at red supergiants, they have a binary fraction of about 20 to 40%. And a lot of those red supergiants that you see that are single are probably stars that used to be a binary system that instead merged on the main sequence and then continued on its life as a single star, and now looks like a single red supergiant. But 20 to 40% of them are still in visible binary systems. For Wolf-Rayet stars, which is another term for blue supergiants, it's at about 30%. But for yellow supergiants, in that area of the Hertzsprung-Russell diagram, the gap where stars pass pretty quickly, there hasn't been a constraint on that yet, which we're looking back to. Okay, and this is really important because in this area of the Hertzsprung-Russell diagram, the Hertzsprung gap, so many interactions can happen. And this is because as stars cool rapidly, they expand. So there's lots of opportunity for that expansion to cause the primary star to start to interact with its partner, start to transfer mass. So types of binary products that we can have in the gap. First, you can have binaries that are wide and don't interact. This is the 20 to 40% of stars that end up being red supergiant binaries. So they don't end up interacting here, and they remain as binaries when they are red. However, there's also lots of other interesting things. You can have stars that do begin interacting in this middle part of the diagram. This is from a really interesting paper that came out a couple years ago that talked about how stars can sit in this area of the Hertzsprung-Russell diagram and burn through helium in the Hertzsprung gap, which is something that had never been thought of before. It was always thought that stars would move through this part of the diagram quickly, not sit there and live out a portion of their lives. You can also have examples of stars that are post-interaction binary products. If you remember, I was talking to you before about a system where a star gives a lot of its material to its companion, and you're left with this tiny little hot strip star that lives sort of over here on the left-hand part of the Hertzsprung-Russell diagram. That star continues to evolve, and it can pass back through this area of the Hertzsprung-Russell diagram in sort of a second stage of its life. These are models of stars that re-enter the gap, but is not the first time it's been going through, it's the second time. So there's all sorts of weird and wacky stars that appear in this area. And of course, as I alluded to before, the progenitors of these peculiar type of supernovae, the supernovae that have lost a little bit of hydrogen, but not all of it, their progenitor stars are yellow supergiants in binary systems, and we expect them to live in this part of the Hertzsprung-Russell diagram. So it's super clear that understanding yellow supergiant binaries is crucial to understanding the complete landscape of massive star binarity. You have to look at this sort of middle ground when stars are in the process of expanding and doing all these interesting things. However, while there have been some local examples of yellow supergiant binaries, so individual systems and individual examples of things that are undergoing interaction, like overfilling the Roche lobe, there has been no systematic identification of yellow supergiants that are in binary systems in the same way that there has been for red supergiants in binary systems or main sequence stars that are in binary systems. So that's where we come in. That is the core goal of the project that I am currently working on, is to eventually come to understand the binary fraction, or how many yellow supergiants are in binaries in the Magellanic Clouds, where, if you're not familiar, the Magellanic Clouds are satellite galaxies of our Milky Way. I like to work there because you get a whole galaxy that is all the way outside, and you can see the whole galaxy, whereas working in our own Milky Way, it's kind of hard to count the forest through the trees. But yeah, so we're working on one grand project to identify and classify all of the yellow supergiant binaries that exist in these two small satellite galaxies of our Milky Way, and eventually lead us to sort of our like special goal for this project is identify a population of these partially stripped envelope supernova progenitors, which has not been done before. So this is a future project. I am at this stage right now. I'm at the beginning stage, and I will walk you through sort of the past year of the project, which made up the last chapter of my thesis, on our initial strides toward doing this, and sort of where we are now and where we're going to go into the future. So the first goal, here are the two Magellanic Clouds that we're looking at. The first goal is to understand what types of yellow supergiant binary systems might exist physically, and can we detect those with the resources that are readily available to us? And for astronomers, that first means photometric data. So just looking at images of the sky, magnitudes and colors of stars, because that's easy to get. And in the Magellanic Clouds, that's optical data from a really nice survey that was done back in the 2000s called the Magellanic Cloud Photometric Survey, which is where they took big wide field plate images of all of the clouds and got magnitudes and colors for every single star, which is excellent. And also UV data, which comes from the SWIFT satellite, which also did a survey of the Magellanic Clouds. So we wanted to systematically search the clouds for yellow supergiants with signs of a binary companion. And previous researchers had done a lot of work actually asking the question of, okay, if you have a yellow supergiant and it's in a binary system, what is the companion? What's the other star? Like, what combinations of stars and colors and masses actually physically make sense? And the answer is actually that they're likely to be B and O type stars. So their companions, if you consider a yellow supergiant as any star that is about 10 to 12 solar masses and larger, that is at this sort of evolved part of its life, their companions by far and away are most likely to be a main sequence star that's between like 3 and 6 or 3 and 10 solar masses. And the reason behind this is actually wild. If you consider instead a star system that forms out of a gas cloud, and you have a 12 solar mass star, this will eventually become a yellow supergiant, and you have a 1 solar mass star, just like our sun, and they start to collapse out of the gas cloud at the same time. By the time the larger star, because remember, larger stars evolve more quickly, by the time the larger star becomes a yellow supergiant, the 1 solar mass star still isn't a star yet. It hasn't finished collapsing out of the gas cloud. It's still on a protostellar track, which is crazy to me. And my mind still gets blown every time I need to explain this to people. Basically, because larger stars evolve faster, you need to have, in order to have a companion to a yellow supergiant that is even a star, that has had enough time to evolve to the point where it is fusing hydrogen in its core, it has to be big enough, which excludes it to the biggest, brightest, and bluest types of stars. So the only companions that you expect to see to yellow supergiants are B and O type stars, which are blue, very bright, and very, very blue stars, which is a little crazy, but is actually super useful because yellow supergiants are some of the brightest stars in the optical wavebands. They put out most of their light, like our sun, in visual wavebands. They are the brightest objects if you were to look at the sky with telescopes that see to similar light as our own eyes. B and O type stars are offensively bright in blue and ultraviolet colors. So these two types of stars put out very different kinds of light, which is exactly what we're looking for. So this plot is a little wild, but it's one of my favorite plots I've ever made, and I will explain what it means. Because there haven't been any searches for yellow supergiant binaries yet, we don't have any real-life examples of the types of stars that we're looking for. So instead, we made models. We would take astronomical models of yellow supergiants and models of their likely companion stars, which are these, I'll refer to them as OB stars, and put them together and said, okay, if you had a yellow supergiant system, what would it look like when you observed it? How bright would it be? What color would it be? And so on. On this plot here, every single little box that you can see is one model that takes a yellow supergiant and an OB star and puts them together. And we had a range of yellow supergiant colors from orange K-type stars all the way up to kind of whitish A-type stars. And we had a range of B-star masses from about 3 solar masses all the way up to 18 solar masses. So basically putting together every single combination of yellow supergiant and OB-type star we possibly could. And then we asked, in all of the various, these are pass bands. So these are filters from J, which is an infrared filter, up through U and V, which are blue and green visual filters, to these M1, M2, and W1 filters. These are ultraviolet filters. How much light from this combined object can be attributed to the companion star instead of the yellow supergiant? So if you consider infrared light, in every single combination, all of the light that comes out of the infrared part of the spectrum from a yellow supergiant binary is coming from the yellow supergiant, because it's much brighter in that part of the spectrum, whereas an OB star barely puts out any radiation in the infrared. But then if you go over to the ultraviolet spectrum, suddenly this part of the diagram is awash with blue. The blue OB star is contributing so much more of the light if you were to look at these systems in ultraviolet. So this is useful. If you were to look at a yellow supergiant all by itself using a blue or an ultraviolet filter, it would look really faint. You wouldn't see very much. If you were to look at a yellow supergiant binary system with a blue or ultraviolet filter, it would shine brightly because of that companion star. This is another, okay, I'm really sorry. This must be a error with the way that the slides, yep. So there's supposed to be more dots there. Okay, this is useful just to start off with, and then maybe I can find a way to fix this. These blue dots down here, so sorry, let me back up. This diagram is showing a color, which is what you get when you subtract two filters together. So this is showing V minus I, so this is a very red color, and it gets redder as you go towards the right. And up here, we'll just look at the top for now, this is U minus B, this is a very blue color. So basically, redder things are in the top right, and bluer things are in the bottom left. So all of these blue dots here, these are our OB stars. So these are our little blue main sequence stars that we think are the companions to these. These are these yellow supergiants that we care about. And in the other version of this plot, which I will try to find in just a second, but if you consider what they would look like if you combine these models together, essentially, if you consider the U minus B color, if you added one of these blue stars to these yellow supergiants, the combined result would be somewhere down here. It would get a little bit more blue. So we are looking for stars that, when you consider red colors, look like a yellow supergiant, but they have too much blue light to be explained by a yellow supergiant all by its lonesome. The only way to explain the amount of blue light that we see from the star is that if it has a buddy, if there's a blue star next to it as a binary. I just want to see real quick. Mike, you mentioned that you had downloaded the...
Yeah,
Yeah, just because it would be really good to have that. Yeah, that's your file folder.
Yes, it's actually on my desktop
Okay.
there.
That top one.
Yeah.
I think it opened in PowerPoint. Okay, and then can I just scroll down real quick just to see if it loaded? It did not. Okay, this is a Windows Mac thing. Okay.
Okay. Sorry about that.
No worries. Okay, so I can show, if people are interested, I can show this to people on my, I brought my personal laptop with me actually, so you can see the full version of the spot. But just imagine that extending down from each of these big orange and yellow dots right here, there's a ton of other circles that have blue lines around them, representing the union of a yellow supergiant with a B-type star together. And they fill the shaded green area of the diagram. So we are looking for stars that live in this area when we look at their colors and magnitudes to identify yellow supergiant binaries and separate them from yellow supergiants all by themselves. This down here on the bottom, the axis here, this is now showing ultraviolet colors. And what happens here, you can see sort of in the little shape that I've drawn here, that the bottom of where these combined models are, especially once you get to hotter, yellower stars, there's not a lot of distance between where those combined models end and where the single yellow supergiant is. So it's kind of hard to tell, especially if you have some error, if you have some uncertainty in these models. What happens for the UV sources is kind of hilarious. They basically go down to here. So there's a huge difference. And that's because yellow supergiants, they don't put out very much light in blue colors. They put out even less light in ultraviolet colors. But these OB type stars, you can even see, they put out almost all of their light in ultraviolet. So the upshot from this is that UV data is actually much more useful than optical data. The issue with that is that UV data is hard to get. You can only take UV images from space. The ozone does a great job at blocking out ultraviolet light, which is great for us humans in general, sad for astronomers, but great for not everyone not having sunburns all the time. So optical data is more widely available, so we start with that, but ultraviolet data is really where it's at. And then I will just continue here. Yeah, so I might talk about a blue excess or an ultraviolet excess. That's me talking about an excess amount of light compared to a yellow supergiant all by itself. So really briefly, we use infrared data to first identify, in order to find yellow supergiant binaries, you need to find all the yellow supergiants. So we made some really broad cuts where we took everything that broadly correspond to yellow supergiant binaries in the Magellanic Clouds. So things that were bright and above about 9 solar masses. So looking at this diagram here, sort of in this area where these crosses are, and things from a range of temperatures. And then, oh, okay. Yeah, this is like my main point. Okay. Oh, the PDF version. Mike, I think if you also downloaded the PDF,
Don't know if I did.
okay,
How'd you send those to me?
Google Drive. Sorry about this, everyone, but everything hinges on these next plots.
Okay, so I need to pull up my
Oh,
So
maybe
where's-
if we stop sharing first.
yeah, so it's over
Yeah, it's over
here.
here, yeah.
Okay. Nobody look while I type my password. There we go.
And then PDF. This is set up. Yes, okay, okay.
Okay,
Yeah,
yeah,
so
probably
full
should I?
screen.
Yeah, so you can figure out how to do full screen there.
Yeah, okay.
Yeah, I guess. Rare time PDF.
Yeah, Mac and Windows don't like each other, which is sad. I will just get this up into full screen. Hang on. Okay, hang on. If I do Google Docs, it might.
Looks promising.
No, I don't want to do that. Okay, hang on.
Okay.
I'm just gonna do this and I will just manually work my way through it. And I will share my screen again. Or actually, are we still seeing that? Okay, perfect. Okay, so rolling back to this briefly, this is what I was talking about. These are these models that are combining this yellow supergiant model with all of these blue stars. And you can see how it drops down in this blue space. And then if you compare it to, this is what I was talking about with the UV models, they're so much more spread out. They're so much easier to see when there's an excess of UV light compared to a yellow supergiant all by itself. So this is my explanation for all this. Okay, so here in gray, laid over the models I was showing you before, all of these little points here are stars that we think are yellow supergiants.
Yeah, good thing you got that slide.
Yeah, this is important. Yep. So okay, so these are all of our yellow supergiants. First of all, there's a lot of stars that are kind of just too hot to do anything with. These were part of this project was trying to find out where's our limit, basically. Where do yellow supergiants become so hot you can't distinguish if they have a companion star or not? So all of these blue points here are stars where basically we're throwing in the towel. We can't tell. They're so far over towards the bottom left of this diagram, you can see some of them are even overlapping with single main sequence stars. So you can't tell if they have a binary companion. So those are a little bit of a wash. These stars up here, these sort of golden ones, are stars where we think that they don't show any evidence of a blue excess. These guys don't show evidence of being partnered with a blue main sequence star. They're up near the top. And then that leaves us finally with these stars that I have highlighted here in green. These are stars that we think do show an excess of blue light. These ones that fall down into this area where yellow supergiant models have to have a B-type star attached to them in order to get this deeper blue color. So very roughly, depending on the exact method we use to sort of make these cuts, we see compared to the entire population of yellow supergiants that we're looking at, about 30 to 50% of them have excess blue light. So I'm very careful not to say we've discovered a binary fraction of 30 to 50% because it's way too early to be making that type of claim.
And it's probably good to mention for some of the people who aren't so into astronomy that down is actually brighter on this graph, right?
So this graph actually doesn't have magnitude on it. It's just color.
But on the left side,
Yeah. So yeah, okay. So more blue light and more, so where it's color, it's a little bit weird. So essentially the number is increasing towards redder light. So the further you go up this, you're getting redder, and the further you go to the right on this, you're also getting redder. So the reddest stars are up here in the top right, and the bluest stars are down here in the bottom left.
that's sort of what I was getting at.
Yeah. Awesome. Yeah, absolutely. Yeah. So this is exciting. We appear to have found yellow supergiants that have blue stars orbiting around them, which is a big, like, order of magnitude increase over the 5 that had previously been discovered up to this point. So this is exciting. However, there's a lot more work to do. Some contaminants are possible. There are some weird types of stars that might wander into this area that aren't yellow supergiant binaries. And there are many uncertainties even in our single star models with exactly where all of these things line up. So there's a lot of work to do in this sort of realm. And then just for reference, this is the ultraviolet. So you can see sort of a similar thing where there are stars that are up the top here, and then ones that fall down further and have all this blue light. But this is essentially showing you the same thing, that the method works up to a certain point, but you can get better results. You have less of these blue stars where we're throwing in the towel, we can't figure out what's going on with ultraviolet light, which is important. So that is sort of the initial part of the paper. That is the first paper where we describe what we do with photometry. We found this group of stars that we think is really interesting, but now we need to find out more. And there's only so much that you can get with just magnitudes and colors. If you really want to understand what's going on inside of a star or in a system, you need to have spectroscopy. And you get spectroscopy from things like the Magellan telescopes in Chile, which I've been very privileged to visit, or the Gemini telescopes, which also have a Southern Observatory in Chile. And we have, myself and my collaborators have been in the process of collecting spectroscopy for all of these really interesting stars, these green ones that we think show signs of a binary companion. We've been hard at work collecting spectroscopy from various observatories around the Southern Hemisphere, in Chile, also some from Australia, in order to collect a big set of data of spectroscopy. And of course, spectroscopy can tell us so much more. So I'm going to walk you through just quickly. This is not our spectra. These are 2 models, but these are the predictions, as I've mentioned up here. So on this diagram, just looking at the top here, the red line is of a yellow supergiant star. In this diagram here, a rather cold one. It's 4,000 Kelvin. Our sun is around 6,000 Kelvin. So this yellow supergiant is colder than our sun. The blue line here is of a 12 solar mass main sequence star. So this is a really big B-type star. And then the black line is the combined spectrum. So if you have both of these stars in a system together, what you would expect to see when you take spectroscopy is the black line. So one thing that you would notice, so the thing that you're really looking for is the difference between the red line and the black line, where those differences might lie. You can see out in the red part of the spectrum, where the yellow supergiant is super bright, it dominates. There's almost no difference between the black and the red line here. But over here, when you get to the bluer part of the spectrum at shorter wavelengths, suddenly there's a lot more light coming from the blue star. And there are these little absorption lines. You can see them right here. These are called Balmer lines, which is a hydrogen line sequence. And hot stars have this spectral feature in them. So if you had a cold yellow supergiant with a blue companion, you would expect to see these Balmer lines, which you would never, ever see for a yellow supergiant that's as cold as 4,000 Kelvin. However, we're not just looking at the cold yellow supergiants, we're looking at all yellow supergiants, all the way up to about 8,000 Kelvin, which is a bit hotter than our own sun, again at 6,000. And the problem that comes from here is that once yellow supergiants start to get really hot, they start to produce their own bomber lines. And you can see the difference between where this red line is tallest and where this red line is tallest. Now, this yellow supergiant is outputting almost all of its light in this part of the spectrum where these bomber lines are. So suddenly, the difference between the black line and the red line over here isn't so great anymore. However, we have a little bit of hope still left. There is a limit. You end up hitting a wall somewhere around here, which is when you transition from violet light that our eyes can see to ultraviolet light that the ozone totally blocks out. But you can still get to this part of the spectrum even with spectrometers that are on the ground, like in Chile. And you can see that because of the influence of the B-type star, the spectrum of the combined system still kind of goes up. It's still increasing. And there are a few of these little tiny absorption lines that are coming from the blue star that you just wouldn't see for a yellow supergiant. The spectrum just flattens completely at this point. So this is really hard trying to find this, but we're hopeful. And now to conclude, I will show you some very preliminary, as in we're not done all of the reduction of this yet, but some very preliminary spectra that come both from the Gemini telescope and the Magellan telescopes in Chile. So starting off with this first one, this is a spectrum. This is a real spectrum. So this is one of the stars that we thought was really interesting. The gap that's here is just because one of the chips at Gemini South is broken, which is sad, but not one that we need, thankfully. And you can see that sort of the tallest part of the spectrum where sort of the top of the curve is over here, which that corresponds to a star. If I fit one of our models to it in orange, that's about a 5 to 55,000 Kelvin star. And you can see that if I fit this model over it, it fits the overall shape of the spectrum here relatively well. But look over here, the model, the orange line totally drops off, but in our real data, we have all this flux that's coming from here. That can probably only be explained by a blue star, and quite a large blue star at that, in order to get these deep bomber lines. So this is cool. I got excited when we saw this come in. Here's another example of one that's a little bit brighter and a little bit warmer. I think that maybe this is like a 6,000 Kelvin star. This is a star that is very similar to our sun in temperature, but far brighter. You can see this log L. This means that this star is 4 orders of magnitude, so 10,000 times brighter than our sun, because it's a supergiant. But once again, you can see this nice form here, but yellow supergiants drop off really significantly around about 4,000 angstroms, and you still see all these bomber lines, which once again are nicely fit by a P-type star. This is a spectrum that comes from Magellan. Now, I will bid you to ignore the wiggles, because the wiggles are not real. This is an issue that we're having with our flux calibration, which is why these are preliminary spectrum. They're not done. This should be flat, but this should remind you of the second example spectrum that I showed you. The peak of the spectrum is all the way over here. The light coming from the yellow supergiant remains high all the way over to 4,000 Kelvin, and it has these huge deep bomber lines that are coming from a yellow supergiant, which is problematic. So this is a zoom in now. We're really zooming in. So again, we think that this is coming from a yellow supergiant that's probably 8, even 9,000 Kelvin, so super, super hot. But what are these? These are absorption lines. If this is just a yellow supergiant, the spectrum should be basically flat after this point. But there are these lines that appear to be absorption lines, stronger than just noise, and they line up perfectly with the locations of absorption lines from our B-type star spectrum. So we do think that even in the case of these really hot yellow supergiants, we can still say something. This is, again, super, super early, but exciting. So to wrap up, some future work. we're not done yet. Finding the yellow supergiant binary fraction in the Magellanic Clouds will involve several things. We need to analyze, I just showed you 3 spectra. We have like 90. We need to look at all those. We need to understand if we have any sort of interlopers, weird stars, or if there's something wrong with our selection method. But eventually we will work our way towards a fraction of yellow supergiants that are in binaries in the Magellanic Clouds. This is an incredibly important benchmark for all binary models moving forward. And we can couple that with how many we expect to be finding from population synthesis models. There are essentially these really, really complicated computer programs that can synthesize stellar populations for entire galaxies and can tell you we expect there to be this many red supergiants and this many yellow supergiants and this many should be in binaries. So we want to compare to predictions like that. The second thing is identify yellow supergiants with partially stripped envelopes. We want to use both spectroscopy and variability. So this is going back to trying to find systems that will eventually become those really weird supernovae that lose a little bit of their envelope, but then blow up before they do anything else. There have been some really promising examples in the literature of people finding very difficult to find, but still possible elements that are indicative of mass transfer happening. It's complicated, but it can be done. So that's sort of one of the cooler goals that I want to look at. And then finally, okay, there's a lot of text there, but I'm going to break this down a little bit simpler. This Saturday at 12 noon, if you turn into CBC radio and tune into Quarks and Quarks, you will hear my supervisor, Maria Drought, talking about a discovery that she made. I was a part of this paper, but it was the brainchild of my supervisor, Maria, a collaborator of hers, Ilva Goldberg, and another student friend of mine, Bethany Ludwig. They identified the first population of stars that are completely stripped of their hydrogen envelopes. Do you remember the little cartoon I showed you earlier with the 2 blue stars, and then one of them ended up a tiny little strip star? We have known forever, basically, that those stars should exist as an outcome of binary evolution, but none of them had ever been found until Maria and Ilva worked together to design a brilliant observing program, and they found an entire population of them. Their paper was published in Science, and if you tune into Quarks and Quarks this Saturday, you'll get to hear Maria talk about it. It is super, super awesome work. I helped with the spectra, so I'm super proud to be a part of that. But basically, if I find these partially stripped stars, I can compare that to the fully stripped stars that Maria and Ilva and Bethany found, and we can say something about how efficient envelope stripping is. How many stars have only lost a little bit of their envelope versus how many stars have lost all of their envelope? And does that depend on mass or metallicity or the plethora of things that can happen in stellar astrophysics? So that one is very cool. And that brings me to the end. Thank you very much for bearing with me for technical difficulties. And
I'm happy to answer a few questions.
absolutely.
Okay.
Okay.
Started using looking at spectra from 2 different times, see if you can see any Doppler shift or anything. Spectra.
Yes, we absolutely want to do that. So the question, just for anyone online, is have we ever considered taking spectra at 2 different times and looking for Doppler shifts, which essentially what that means is if you have 2 stars that are in a binary, they're rotating around each other. So if the camera is our telescope, at some times one star will be moving towards you and the other will be moving away. And then at other times it's the opposite. So you will see redshift and blue shift in the spectral lines. We definitely want to look at that. These are yellow supergiant binary systems. So the primary star is kind of large. So the orbital periods are on the order of years. So this would be a much longer term project where we need to go back year after year to take spectra. But that's an excellent question. We super plan to do that.
Hey, Tyler?
Yeah, so up a little higher, you had we were looking at the teal green candidates that
Yeah.
could be in the future of the class stars,
Yeah,
and the yellow supergiants.
these guys.
And it was in ultraviolet, I think.
This
is
one.
the one.
Yeah.
Perfect. So here between the large Magellanic and small Magellanic, you see at around 1.5 minus that magnitude, you have this really long tower of sort of a cluster of candidates. Is that unique to the SMC? Is there something going on there?
You should be a reviewer. So that's a good question. So you can still see this feature actually here.
Yeah.
It's this big clump. There's more of a clump here than there is in the LMC. So part of that is to do with metallicity. The Large Magellanic Cloud is about double the metallicity, or the amount of, when we say metallicity in astronomy, we're talking about any element that is not hydrogen or helium. We're really weird in that way. We're like neon and argon we call metals, which it's a sin of astronomers. I don't know why we do it. But so there's more metals other than hydrogen or helium in the stars that are in the Large Magellanic Cloud than the Small Magellanic Cloud. And that has a consequence of making stars hotter. Yeah. So that's why you see more of these hot stars that we can't do anything with in the LMC than in the SMC. So part of that is just that there's more stars at different temperatures, which is why at differing temperatures, which is why you see this clump in the SMC and not so much in the LMC. As to why it's specifically happening at this temperature, why there's this big sort of tower here, I have no idea, and I'm trying to figure that out.
I guess, yeah, my own thought is, do they get hotter without also increasing luminosity? Do they simply increase in temperature, or?
So something has to change. If you get hotter without increasing your luminosity, you have to shrink.
Right.
Your radius has to change. Now, if some of these stars down here are undergoing binary interactions, that can do all sorts of weird things. And then, you know, as I saw mentioned earlier, if you have something that's actively undergoing interaction, you can drop the luminosity of these stars off a cliff. So the stuff that's further down here is definitely like the weirdest stuff that we want to look at. So maybe there's some stuff going on here, but as to what the identity of this mystery clump is, I actually do not know.
Oh, that's a great answer. Thank you very much.
Other questions? If not, oh, Robert?
I was just wondering, you said that 70% of normal stars are in binary systems, and then 70% of those have interaction.
Mhm.
I think that was it.
Yep.
And, so I was just wondering, from the point of view of Star Wars, that would have to be like one weird system, right?
Yes,
A very small number would be able to support life.
exactly. Yeah. So the number is 70% of massive main sequence stars. So if you consider stars like our own sun, you might think then, well, how is it that we have a single star and not, you know, chance of having a binary? But the 70% number is only for really big stars. If you consider solar type stars, the binary fraction drops to about 30 to 40%. So and then because the stars are smaller, they have to expand so much more in order to undergo interaction. So necessarily for the types of stars that you might expect to have a planet that humans can live on around, because life around, you know, an O and B type star like this put out such an offensive amount of ultraviolet light, even, you know, a sturdy atmosphere around the planet would not be able to hold up very long.
And they don't last long enough.
They don't last long enough.
Yeah,
Exactly.
I mean, we needed a star that was going to last billions of years.
Exactly. So for those types of stars, solar type stars, the binary fraction is a lot smaller, and then even then the interaction fraction is a lot smaller. So George Lucas actually wasn't too crazy for having Tatooine be a binary system. It's actually not, it's not too bad.
That's not the reason he's not crazy. That's just one.
Yeah.
Okay, well, thank you very much, and thank you, Kate. We may already have the calendar, but this is, oh.
Yep.
And any updates on the gamma ray burst question?
Okay, my first question.
The question you were asked on the gamma ray burst. You don't want to talk about it?
No, I don't know what you're talking about. Sorry. Oh,
Yes.
okay. This is just a dad brag moment. I am not the lead, but I am a co-investigator on a submission to use the James Webb Space Telescope to do something not related to my research. It's about gamma ray bursts and other things, but that's just dad wanting to talk about me possibly getting to swing JWST around, which is cool. And I have to say, it is my secret plan, totally not because I absolutely love it, but it's my secret evil plan that the reason that I give these talks is to get this calendar every year.
That brings me to my next point. We're happy to supply you with a calendar every year. You have an open invitation whenever you're in town.
Yes.
Just give whoever's in charge. It may be me, it might not be someday, we'll see.
Yes, and
But you're always welcome to come and tell, and we're getting used to Anna giving us amazing talks, but people who aren't academics probably don't appreciate how amazing it is that a relatively young researcher can give us a talk every year, and every year the talk is so good and so different. I mean, for your career to be on that kind of trajectory is just amazing. So thank you again and good luck. I'm gonna, maybe I'll just slide my stuff over here and maybe this is the way I should have been doing it for the last 3 years. So I'm gonna lower that. I'm not gonna turn off Zoom yet. Lower that. And then I'm going, oh, you know what? Somehow we closed this, but that's okay. I can fix that. I'm gonna slide that over there and Randy's gonna tell me if he can see it. In a second. Or people online, can you see this? That's there, okay. So thank you. You've also taught me how I should have been running my meetings for the last couple of years. This is much nicer. Okay, so I'm gonna go through some observations very quickly. The last month, there were a couple of nice days and we had kind of a festival of Jupiter. So some solar system objects, Cynthia and me took pictures of the moon on November 16th, and then November 21st, I took a shot of the moon, and then Cynthia. So you see, we did some shots of the moon. Won't bore you with that. And then Chris did an amazing shot of much closer up Gassendi. That's Mersenius there, right? That's you, right? And it's spelled Billy, but I'm sure it's a French name. So how do you actually pronounce that?
I've actually forgotten,
Say it with a French accent anyway.
I'll fix the caption for this.
Yeah.
Dark Billy is fine.
Yeah, okay, and we had a lot of shots of Jupiter, so here's one. And they're all sort of grouped around the same few days. Chris with Io and its shadow and Ganymede. So this one is actually over a couple of hours, but you can see it's Ganymede over here and Europa on its way out and Io on its way in. So those are just 3 images separated by a couple hours. These ones are separated by 8 minutes, but I thought it was cute that you could see things move a bit. And then this one is actually over an hour and 15 minutes, and you can see the red spot moving across. And then we get into some with Chris and just some beautiful intense colors. So this is Jupiter and Io. So see, these are all within a few days. We had a little clear window in November. This is the same night, but with looking at the moons on the other side. And then this is quite significant because Tim, this I guess is like first light for Sue Hart's observatory. Here it is. That's an 8-inch, right?
Yeah.
Schmidt Cassegrain. So it looks nice and neat. Does Gary and Chris, do your observatories look like that inside?
No.
No, okay. I didn't think they did.
So excited.
And so Tim and Sue collaborated on this one.
It's a really wonderful observatory. You definitely have to go out and see it. It's beautiful.
Okay. We'll have to take turns going in. We probably can't all fit in at once. Okay, so then just a few days ago, well, a week ago now, I guess. Ish. Chris got another nice image here. And which side is which? Do you know which one's is this scanning? Oh,
I think Europa and Ohio. Europa and
okay. And then okay, and then this is a little bit later
Yeah, it's after supper.
after supper. And Saturn. And then Uranus. And Chris did a few shots of Uranus, and those of you on the talk list may know what's coming next. And that's Uranus with the moons, which is, I think we were all pretty blown away. And then Chris also fiddled around with, actually did so that's Uranus there. So this is an image on the planet with less exposure, and then the moon's more, and then put together and sort of masking the overexposure around
Yeah.
Uranus.
You already get the moons to register 2 seconds per exposure for a lot of frames. And so it's just nothing you can do. There weren't enough sharp frames, so the moons are going to be fuzzy, but quarter-second exposures for Uranus. So
Yep, so that's pretty amazing, and this is stellarium to show where those moons are. So Umbrio, Titania, Miranda might be in there, but that's probably Ariel. Miranda would be in
Yeah.
there, and Oberon.
I'll try again to bring it out or get more data. Probably get more data.
Okay. And this is Neptune and Triton, and I actually fiddled this a little bit in PowerPoint to try and bring out the moon there.
Yeah, I need to redo that, because it's in the data, but.
Yeah,
but
it's
thank
so
you
it's
for-
there.
Thank you for bringing it up.
And we had the Geminids, so Jim got a couple of Geminids down by Pleasantville, and Gary, of course, got all of them. So this is Gary's, and what's that? That's an airplane, I guess. But
Starry image.
so most of those are Geminids, and that one
Yes.
must be something else, right?
Pretty cool.
So this is Gary's meteor camera. And then some deep sky objects. So again, I'm sort of going from higher RA down to lower. And so we're sort of running out of the season for things near Cygnus, but I tried M39, which is an open cluster. So it's here's Cygnus, so that's Deneb. And there's M39. It's not super impressive, but it was what was away from my neighbor's Christmas lights. And then we had a couple of contributions of the Cone Nebula, the Christmas tree cluster. So here's Orion, Auriga, and Gemini, so it's kind of in that neighborhood. And the Cone Nebula and the Rosette Nebula are both in Orion's armpit kind of area. And so the Cone Nebula, there it is there. This was Jim Johnson's image. And this bright star is S Monoceratus. I think that's that one, right? And you can see that it's sort of lighting up the edge of this dark nebula. And then Robert did the same thing. It's just oriented a little bit differently. And Jim Johnson also did the Rosette Nebula, which is nearby. And there it is there, a lovely shot of that. And this is, this one, yeah, this is First Light with his RASA telescope, which we're going to get a talk sometime next winter about what a RASA telescope is. Extremely fast telescope. And he also did the region around, so this is the belt of Orion, So around the Horsehead Nebula, you have the flame, or around Alnitak, you have the Flame Nebula and the Horsehead Nebula. And then, of course, we have the Orion Nebula and all the nebulosity around here. So we got, this is starting to be the dominant constellation, sort of once you get past about 9 or 10 o'clock at night. So we're going to start seeing more and more of these. So this is Jim's lovely. So this is one of his first light images with the RASA telescope, the Horsehead Nebula, which is the Horsehead Nebula is Barnard 33, I guess, in front of IC 434 is the red part, and the Flame Nebula, and there's Alnitak. You can really see the horse, and then Robert got a nice shot of the Orion Nebula, and then Jim got just amazing. So the title for this, I guess, when it was posted was Demarin's Nebula, which I guess is the sort of jellyfishy looking thing in there. But of course, there's a lot more there. There's a Running Man and M42. A lot of processing there to bring out all the nice filaments and dust and stuff. Lovely job, Jim. And then Robert did the Crab Nebula, and it's M1. So again, it's between Auriga, Orion, and Gemini. It's a supernova remnant, and a lot of detail in the filament there. Nice work. And then Jim Johnson did the California Nebula, which is quite faint. So here's where the Pleiades would be, and it's and there's Auriga and Orion over here, and Cassiopeia, so just to orient you. So the California Nebula is here close to Perseus. And again, this was one of his early shots with the RASA telescope. So we're going to hear about that coming up. And then we had some shots. So here's Cassiopeia. There's the double cluster. So over on this side of Cassiopeia, there's the more pointy side of Cassiopeia. The Heart and the Soul Nebula, we had some contributions from there. John, I think, sent in the Soul Nebula. It's an emission, they're both emission nebulas. So there's John's Soul Nebula, very nice. And then Jim did a bunch of versions of the Heart Nebula again. So this is, so the ones I've actually labeled as first light were all on November 21st. That's the first shot he had with this RASA, and which is basically, it's a very fast scope. So this is sort of more, if there's such a thing as normal color when we're doing this. And then this is the same thing with the Hubble palette, where it's sort of looking at oxygen and sulfur and color coding them. If that's the right way to describe that, or oxygen, sulfur, hydrogen, oxygen. And then there was he did the same thing again with a slightly more aggressive or extreme version of the Hubble palette. So these are all the same image, but just weighting the colors, weighting the what came through different filters differently. And then the Pleiades, Chris did some things around the Pleiades. This is Alcyon, and then these are the Pleiades, and that's Alcyon there, right? Is that?
If you zoom right in, you can't see it on this, but there's the top frame is hugely magnified. I just pointed the telescope. This is after I did Uranus, and before I shut it down, I just did Uranus exposures on Alcyon.
Yep.
So it's like F20 at ratio of 20 over 12 inch telescope. So it's 6,000 millimeters or something local. But anyway, it's, yes, there are stars there that are in planes that are more than the right ones.
Yep.
That's
And
your thing about the Hubble palette, by the way, hydrogen and H alpha is red, sulfur 2 is red.
yeah, so they have to separate.
So they make hydrogen green in the pseudocolor, and then you see all that one.
Okay, and we often have an Andromeda, but tonight the contribution we have in this part of the sky. So there's Cassiopeia, there's sort of the big square bits up there. So the Andromeda Galaxy would be here, and the Triangulum Galaxy is down near Triangulum. Contributions from Gary. So only 29 minutes here, but there it is, and we're seeing more and more of these. What's that?
50mm optic.
Yep.
Half of an off.
So amazing. And so that's the end of the observation reports. And so Robert, do you want to do a really quick sky this month?
No, but you wait. You're there.
Okay.
Pronounce Robert's favorite word.
Niximion or something like that. So the sunrise, sunset, they aren't very far apart anymore. There's the sun today. Oh, lots of action.
Nuts.
And I guess it was sort of out today. So Jupiter and Saturn, we've just seen. Saturn, we're kind of getting to the end of Saturn season, but Jupiter is quite prominent. Uranus and Neptune are up there. Venus is still a morning object. Yesterday was first quarter, right? Was it yesterday?
Yesterday or 2 days ago?
Maybe 2 days ago. It was pretty recent. And here's the planet roundup, but we just sort of talked about that. So comets, lemon, this,
I'm very excited.
yeah, so H2 lemon, I guess, is starting to be visible. And the other ones I think are, that looks pretty tough, 11. So, but there is one that's starting to be interesting. And if you're a morning person, then I guess this one is, Su Shin Shan is maybe visible. We did just have the Geminids, and I guess is it Ursids or something that we're into?
Down there in the red.
Oh, there it is. You hit it. Yeah, so that's where we're sort of into that or coming into that right now. So that's sort of medium. But you know, it has to be clear for that to work. Some space station, they all look pretty early in the morning. Robert has picked out some binocular and telescopic objects, and the challenge is something in Camelopardalis. And we haven't been going out to Butterpot, but and maybe it's getting a little cold for that. But it's warm tonight. So well, it looks like it was, well, according to this, it was yesterday. So this is December. The full moon's going to be day after Christmas. And so that's it. So I'll lower that one and wrap up. If you haven't paid for calendars, you can send it in. The next week meeting is in January. Please, everybody within the sound of my voice, vote on the AstroImaging contest, because I want to have enough votes so that we actually know who won. There's some very impressive images there. If you have any issues signing on, let us know through info or email me, but info@St. John's. Yeah,
Like, are there votes in each category?
yes,
Okay, so.
yeah, so you,
You can vote for more than one.
yeah, so
One in each category. Yes.
let me just bring that up again and show you the poll, because now that this is what you will see. And so you can do one vote for wide field, one vote for solar system, and one vote for deep sky. So there, to actually see the nice sized images, go to the website, and you can just click on the front page of our website. Craig has set that all up, and there's some information about the images if you want. And I've just sort of put thumbnails in here so you remember which one you're looking at. Okay, and so it's January 8th. Well, we're looking to sort of wrap it up that week and then get little plaques and certificates and stuff done for the next meeting. Okay, so thank you, everybody. Thank you all for coming. And we have some refreshments and I guess there's some coffee over there. There's some pop. There are some wraps and a cheese tray that if you give us a few seconds, we'll spread out. They're in with the cooler with an ice pack. There's some fruit, some stuff that's not very healthy for you.
Yeah, even all the way down to,
Yeah.